Friday, what we're going to do is we're going to continue on loops, probably finish it up with a couple of exercises that will bleed into next week. Next week we'll wrap up loops and do a couple of other things, and then prep for eventually for your exam in the fifth week. Right. More details on that will be posted next week, the week prior to that first exam. But otherwise, we left it off with what's the difference between a for loop and a while loop? Well, structurally, they're a little bit different. Now, let me make sure that I'm actually broadcasting here. Yeah, we are. It's just really, really quiet. All right, there we go. So, yeah, we are online. If you have any questions, you can go ahead and post to Piazza. You can post to YouTube there, all right? So which loop is best? Well, you can always rewrite one loop as another loop and vice versa. It's just that it's more natural to use a for loop when you know up front that you've got this iteration that you're going to go for 10 iterations, 20 iterations, or generally some variable number of iterations, but a discrete number of iterations. And generally you want to use a while loop when you don't know up front how many iterations you're going to go. Like the example that we developed last time, where we want to determine how many digits there are in an actual number, in an integer number. And we have to divide by 10 until it is 0, right? And so if we knew that up front, then we'd have our answer. And so a while loop is a little bit more natural here. Of course, you could, rewrite this as an equivalent for loop very easily. I won't bother showing it, but I'll leave that as an exercise to you. But you can do it, right? You only need one type of loop. You can also nest loops. And what I mean by that is, let's go ahead and go over here to our code editor. That reformat A-style also thinks I want 4 spaces for indentation. I prefer 2 because I don't like long lines and stuff like that. But what I mean by nesting is we can go ahead and let's establish a variable here, 10, right? And we can have a traditional for loop, an idiomatic for loop here. For int I equals 0, I is less than 10, n, in this case, I++, printf, I is equal to %d end the line. We've seen this before, right? This is going to print numbers 0 through 9. Right? But what I could do inside this loop, since I can put executable code inside of it, I can go ahead and put another loop inside of that. For int, now can I use I again here? I could, but then I would have 2 i's in scope, and which one is which? It'll allow me to do this, probably in both languages too. Here, I'll show you. I is less than n, I++. Right? And we'll print out I. Right? I'm not going to actually run this. I'm just going to go ahead and show you that it will compile, and it's perfectly fine with that. I wonder what would happen if we did that in Java. Ignore that that's for later, right? All right, well, other than the system.out.printf, right? Can you do that in Java? Nope. So what happens in C? In C, inside this for loop here, this I is referring to this I right here. I don't know if there's a way to refer within this inner for loop here to that variable outside of it. Not off the top of my head, at least. So there may not even be a way. But you can't even do that in Java, thankfully. Right? You shouldn't do it here either. What should we have done? We've been using I because we're iterating in a loop. That's our iterator variable. That's our index when we eventually go to arrays. But it's just a generic variable, I. So what comes next? J. What comes after that? K, if we need one, right? And we'll do that here in a second. It's not very clever, right? There's no mystery to it. Why is C++ called C++? Well, this programming language is called C, right? What's one more than C? I++, C++, right? Haha, right? It's not clever at all. There we go. And why is C called C, by the way? Does C stand for anything? No. There's a programming language called B. So they just name these things because naming things is hard, right? All right, let's go ahead and actually run this. How many iterations is this actually going to run? The inner for loop here, we refer to this one as the inner for loop and this one as the outer for loop. The inner for loop here is going to run for j running from 0 to 9, right? But it's going to do that for each iteration of the outer for loop here. So in total, how many lines am I going to end up printing? 100, right? And we see 0, 0, 0, 1, 0, 2, 0, 3, et cetera, For for I being 0 here, it's going to execute those 10 times, 0 through 9. Then it increments I and goes on and does the inner for loop completely again, j. It goes all the way to 9, et cetera. So 100 times there. I'm not. I'll go ahead and pump it up to 100 here. How many lines of output are we going to have now? 100 times 100, right? Which is 10,000. Now how many? Thousands, we call them millions, right? 10,000 10,000s. 100 million or something like that? Okay. Let's benchmark it. And by benchmarking, I mean, let's go ahead and determine how long this actually takes. So I'll go ahead and just do it for 100, right? A.out. Oh, it got done pretty quickly there. Now, things are I/O bound. In other words, input and output to a screen or from a keyboard is one of the most inefficient things you can do in a computer, right? So what I'm going to do is I'm going to make this a little bit faster, and I'm simply going to keep a counter instead, in long count. We haven't talked about longs yet, but a long is a 64-bit integer. It's able to hold way more than 2.147 billion. I'll go ahead and start it at 0 here. And every time I execute this loop, I'm going to go count plus plus. And at the end of it, I'm going to print f what my count is. %d end the line. Count. There we go. So now I'm no longer I/O bound because I'm only doing one output at the end of this entire process. This is kind of a stupid process because it's just counting, right? Oops. LD, I think? Yeah, there we go. There we go. All right, instantaneously. In fact, if you want to, you can actually use a utility called time, and it'll actually time it and tell you that in real time it was 0.002 seconds. Right? For the system time, it was 0, and for your user time, the amount of time that your program was actually running on the computer, it's 0.002 seconds, matching the reality. Right? I think that there's only one processor allowed on AWS here, so we're a single processor. But my computer here, of course, is i9, which I think has 8 cores, and with multi-threading, you can get 16. Don't quote me on that. Most of you will have laptops that have at least a Duo, Intel Duo, right, sticker, and to a quad, right, things. All right, so let's see if we can speed this up. What's its behavior when we've got 1 million instead? It's going to take longer, right? At least that's what our intuitive notion is here. All right, it took about double the time, a little bit more than that. Let's go up to, that's 1 million, 100 million. There we go. Okay, so now we're on the noticeable end of fractions of a second. Nearly, what, an eighth of a second there? Let's go up to, that's 100,000. 100,000 times 100,000 is what? 10 zeros, so that's a 10 billion. How long should we wait for this? I went up an order of magnitude, 10 times. But remember, we've got 2 loops here. It'll be 100 times slower. Right? What was it before? 0.16 seconds. What is it now? Almost 16 seconds. 100 times slower, right? Yeah. All right. What if we went one more? How many is that? That's 1 million millions. We call them quadrillions, something like that. So estimate the time that it will take to do that. Well, if we went up by an order of magnitude, and we've got 2 loops here, it's going to be 100 times slower. 16 seconds times 100 is what? 1600 seconds, 2 hours. A little less than a half hour. Are we going to sit here and wait for that? Nope. By the way, is 1 million a small number, or a big number in computing? No, that's small potatoes in computing. If I went up to 10 million, that's still small potatoes as far as computing is concerned. But we would be going up by another factor of 100. How many hours do we have now? Almost 2 days, right? Another factor. And that means that we go up by another 100 factor, right? And again, this is getting up there. But in the world of computing, no, that's small data. Right? That's not big data. But it would take what? Not hours, days? Almost a half a year, right? Weeks. How many weeks is that? Yeah, over a half a year, right? To get that done. Now again, I'm not doing anything here other than counting, right? But if I was actually doing something, it would take even longer, right? Because all this is doing is just adding one, add one, add one, add one. If you were doing something more substantial, it'd be even slower. So the takeaway here is this kind of behavior is probably not great in practice, right? For practical, larger scale data. We'll understand that a little bit later when we start talking about efficiency, okay? But otherwise, that's a nested loop there. Right? So you can put a loop within a loop, right? You can have, we refer to them as the outer loop and the inner for loop, or the inner loop. You can do while loops as well, right? You can do as many as you want. 3 or more nested loops, and now you're talking about factors of 1,000 instead of 100 when you go up in data size. So if you're doing 3 or more, rethink what you're doing. First of all, it's probably not going to be very efficient, but second, there's probably a better way of doing what you're doing. There's the code. And again, remember that it works in both programming languages as long as you don't copy pasta and forget to change all of your I's to J's. And then if there is a third loop, then you go to K. But if there's anything beyond that, L. Is L a very good variable name? L, L, L. Sometimes it's difficult to tell the difference between a 1 and an L. That's why font families are choosing a good font for coding is so vitally important. Now this font, I really like this font because that L is very, very different from that 1, right? It is very obvious that those are not the same things. But in some font families, right, especially that are used in code, it is not that apparent at all. Right? So even font choices are important. More nested loops is what's called a code smell, right? It's not necessarily bad, but it kind of stinks. And if there's something that kind of stinks, probably it's something rotten, and it's probably something that you need to address, right? That's a term that we sometimes use. Let's do enhanced for loops before we get on to the other smells, right? The pitfalls. This is for Java only. In Java, if you have a collection, that is an array or list, you can iterate over it using a for loop, or you can use an enhanced for loop, which is basically a for each loop, for each loop. But some programming languages do have the keyword for each. Java does not have that. Instead, they call it an enhanced for loop. Don't ask me why. It's probably something to do with being able to, patent it or something like that. They thought at some point that they could patent the idea, even though it was prior art. Everybody knows what a for each loop is. So what I've got here is a list of integers, but I also have this array here of strings. If you've seen arrays or if you've seen lists before, great. If you haven't, don't worry, we'll get to it eventually. The traditional way that you can iterate over these things is a regular old for loop. For int I starting at 0, oops, I is less than, say, args.length. Right? That tells you how many elements are in that array, I++. Right? What I'll do is I'll get the ith element from args, which is a string. S is equal to args sub I. And then print it out. System.out.println S. There we go. And that'll work. That uses a traditional for loop. Oops. I didn't provide any arguments here. So let's go ahead and rewrite that for the list of integers so that we actually have something to work with here. Numbers, dot, and for a list, it's going to be size instead of length. Now get the ith element from numbers. This will be numbers.getI instead of the ith element. There we go. What are you complaining about? Oh, that's not a string, it's an integer. X and X. There we go. So the first one won't print anything because I'm not giving it any command line arguments, but the second one will print everything in this list. 1, 2, 8, 4, 6, 3, and 2. And you see it right here. Right? I can rewrite each one of these as an enhanced for loop. For each string S in the collection args, I can go ahead and just print it out. System.out.println S. There we go. There, it's a lot cleaner loop there. No index variable, no increment, no bounds checking, right? If you just want to print it out, you can use this enhanced for loop if you don't care which element it is. Likewise, you can do it for any collection, including lists. For integer X in the collection numbers, this is how you read it, right? System.out.println X. Much cleaner. I don't have to get the ith element, it automatically is given to me. Right? And we'll have the same exact behavior here. It prints out once, and then it prints out a second time. Right? So those are enhanced for loops. I'll go ahead and make sure that you've got this in your notes so that you can check it out. If you just want to iterate over a collection and you don't care about the index variable, right, then this is the way to go. In fact, we'll look at maybe later on, this is the preferred way of doing stuff because you don't know that your collection is efficiently retrievable. Getting the ith element, that might actually be expensive. Right? It's not expensive if you use this kind of loop instead. Okay. Okay. So back to code smells here, right? I'm going to show you some things that stink, right? Again, they're not necessarily bad, but certainly the things I'm going to show you that stink are definitely bad, right? So pitfalls. Consider the following code. Does it smell? Does it stink to you? I'm getting a whiff of something. All right, well, let's take it over here to our VS Code. Right. There we go. GCC demo.c. Oh, okay. GCC doesn't think it stinks. Its nose is stuffed up. I'll show you how I'll unstuff its nose here in a second. What's it going to do? Is it running? Yeah. Is it doing anything? Nope. So what's the stinky part? This guy right here. What's that semicolon doing there? It's just like the for loop. It's just like the an if condition where we misplace a semicolon. I is 0, while I is less than 10, do what? Nothing. Right? That's what the semicolon is doing. Nothing. So do nothing, do nothing, do nothing, do nothing. Okay? Let me go ahead and roll this back to the original. Now I'm stuck in an infinite loop here. How do I kill it? Control C. There we go. Let's go ahead and unstuff GCC's nose here so that it can start smelling our code. Remember we called this a linter, right? The WAL flag. Warnings, tell me about all of them. Once I turn that on, I get this warning, wait a second, that stinks. The statement, it's misleadingly indented as if it were guarded by this while statement here. Are you sure you meant to do that? Right? It's not going to give you a direct message of, you put a semicolon there, you probably shouldn't have. Right? It's just going to give you this techno-babble of, it's not guarded because it's not bound to it, et cetera, right? But it looks bad, right? It smells bad. It is bad. Right? I wonder what happens in Java. Genuinely, I wonder what happens. System.out.print f. Not so much as a warning, right? What happens? Also an infinite loop. In this case, it's do nothing, do nothing, do nothing, do nothing. To kill it, stop sign. Right? So no, not even a warning there. Right? So the above results in an infinite loop. Make sure that you are properly using your GCC to its fullest using the wall flag. It will catch simple, stupid mistakes like this. Here's another code smell. Looks like it stinks. What's missing? While I is equal to 0, or I is equal to 0, while I is less than 10, prints it, 0. Did we make any progress towards our termination condition? Nope. Predict, without me running this, what this is going to do. 0, 0, 0, 0, 0, 0, 0, 0, 0, forever, right? You're not making any progress towards your termination condition. Here's another piece of stinky code. Fine, I'll restore that I++. Keen eyes, what's missing? No? Curly brackets, even though I've indented, right? So this is very Pythonic, right? Python, do you have opening curly brackets, closing curly brackets? Nope. Instead, it relies on indentation, right? You would be doing something like right if this were Python, but it ain't right here. GCC, demo. What's it going to end up doing? Same exact thing as before. 0, 0, 0, 0, 0, 0. We are making progress towards our termination condition, but that's not part of the while statement. If you do not have opening and closing curly brackets, the while statement only does the next available executable statement, and that's it. Right? It doesn't do the entire block of code. This is not a block of code, right? This is a block of code. By putting in proper opening and closing curly brackets, now it's a block of code. And now it will work. Right? There we go, 0 through 9. Do not get in the habit of not writing these. Sometimes they're not necessary. If you only have one statement, so be it. You don't technically have to put those curly brackets. Right? Don't get into that bad habit. Right? Always put the curly brackets regardless of whether you need them or not. Right? And that's both languages. It's best practice to always write them even if you don't need them. And finally, the one that I like to just show every year is the Zune bug. And I'm quickly getting to the point where nobody is going to know what a Zune is. Are we there yet? Does anybody know what a Zune is? All right, 1, 2, all right. Tell us what a Zune is.
Like the Microsoft iPod?
It was the Microsoft iPod, exactly. MS iPod. There we go. It looked like that, right? It was an iPod before touch. It wasn't even a touch screen. That's why it's got the control down there. iPods weren't touch screens yet either. But it was a cheaper, I think it was $100 less. It also had a radio in it. So they were trying to compete with Apple and the iPod at the time. Well, turns out that on December 31st, 2008, every Zune froze for exactly 24 hours in the entire world. Why? 2008, as maybe you tested on Tuesday, was a leap year. It's divisible by 4, right? It's not divisible by 400 or 100, but you know, those other things, right? So it was a leap year. Tell me about December 31st in a leap year. What day is that? 366th day. Let's take a look at this code that was in a subsystem in the Zune system, right? While days is greater than 365, so it's 366th day, right? So this will be true, and we enter into this while loop. The purpose of this while loop is to check to see if it's a leap year and then decrement 366 to start over at January 1st and then the next year. Add 1 to the year, 2009. Let's continue seeing if it works, right? Is 2008 a leap year? Yes. So this if statement executes. If days is strictly greater than 366, was it? Remember, it's the 366th day, not strictly greater than. So this block does not execute. There is no else. We don't execute this else. So where do we go? Right back up to the top. Right. Did we make any changes? Nope. So what happens in 24 hours when it becomes the 367th day? Still greater. It's still a leap year because we didn't change the year from 2008. Now 367 is strictly greater than 366. So what happens? We decrement, the year increments, and we move on because we've decremented it down to day 1, January 1st, 2009. It took 24 hours to get there. Why? You weren't in an infinite loop. You were in a 24-hour loop, right? Now, the Zune, again, wasn't all that popular, and it was not a system, you know, a critical system where lives were at stake. You just couldn't listen to your music for 24 hours, right? But at the same time, think about the man hours that went into, or that were wasted by going through this bug, identifying the bug, pushing a fix out, dealing with customer complaints, etc., right? Maybe $1 million was wasted in cost, right? Now imagine the same bug in a system critical thing like, you know, medication delivery, right? Can you afford to have your insulin go offline for 24 hours if you're severe diabetic? No, right? If it does, then that's the end of the show, right? And there have been plenty of bugs like that throughout history, where you know, the Mars rover, right? 2 of them, in fact, crashed into Mars because of small software bugs like this. One of them was a failure to convert from English system to metric, and so it was going at X miles per hour instead of X kilometers per hour, way faster than it should have, and it crashed into Mars, right? Those are very, very simple bugs that you can easily take care of. You did it yourself, right? On Tuesday's lab, right? You were testing things. You were writing tests and, you know, probing your code, trying to break your code, right? What obviously did they not test? They didn't test for what happens on the last day of a leap year. What happens on the first day of the leap year? What happens in the middle day of a leap year? What happens for those 3 test cases in a non-leap year, right? All they had to do was write 6 simple test cases to have pretty much 100% code coverage there, right? When we come back on next week, we'll start doing some, I'll give you an introduction to unit testing with what we've been working on so far, right? And that would have been way cheaper than that $1 million that they lost. Right? Again, I'm just pulling that number out of the air. Right? Okay. Let's see. Let's go ahead and do some exercises with our remaining time here. The first one is always a classic. FizzBuzz. Anybody ever heard of FizzBuzz before? All right. So it's a classic because of Jeff Atwood. FizzBuzz, Jeff Atwood. You will not maybe know the name, but you'll certainly know his website, stackoverflow.com. He started it. I don't know if he's involved with it anymore. But where's his actual article? Coding horror. There we go. Why can't programmers program? This is actually in your suggested reading for this week, or maybe it's next week. But here is the statement of FizzBuzz. Write a program that prints the numbers 1 to 100, but for multiples of 3, so 3, 6, 9, 12. Print fizz instead of the number. For numbers that are multiples of 5, print buzz. 5, 10, 20, 30, right? 25, 30, right? For numbers which are multiples of both, so 3 and 5, so like 15, 30, 45, 60, print fizzbuzz instead. And this is a classic problem. I mean, he was writing about this in 2007, but the problem goes back even further than that, right? And it's a weed out question, right? So somebody goes in for an interview and they claim that, yeah, I've got a 4-year degree. I've been programming since I was 3, whatever boasts they want to come up with, and go, all right, here, fizzbuzz, right? And if they can't program it, you know that there's something going on there, right? Or if you read about some of the testimonials here, some people could do it, but still with bugs. A simple program like that would have bugs without them even thinking about it. Or they would do the program, but it took them an hour to do it, right? That's why it's a weed out question, right? It's an interview question that you give to somebody, and you can eliminate, they're probably being hyperbolic here, but 199 out of 200 applicants, right? It's a way that you can get rid of the folks that don't know what they're doing. Something that if you take a computer science course, some of you aren't even familiar with this problem, and so you've done it before, but in the 3rd week, you can do this, right? We're going to do it together. Java, C, it doesn't matter. The only difference is going to be the print statement. Exact same syntax for everything. So help me out. Write fizzbuzz. So if I'm going to go print 1 to 100, what kind of a loop do you want to use? For loop, because you know exactly how many iterations you're going to go for. Instead of starting at that idiomatic 0, though, where should I start? 1. While I is less than 100, is that correct? Nope. I want to go up to and include 100. And I'll go up by 1s, right? I++ here. Okay. So help me out. What should I check for first? I'm probably going to have an if statement, right? If I is divisible by 3, then printf fizz instead. Now that ain't code. It's pseudocode, right? Fake code. Yeah, go ahead. Mod 3 has a remainder of 0, in other words, equals 0. Right? Looks exactly the same when you do buzz and 5. Okay, something's fishy about that already. If this condition, if this condition. You either print fizz or you print buzz. Sometimes you print fizz buzz, but we'll take care of that here in a moment. Should these be mutually exclusive, or should it be that the case that you could do the first one and then you could do the second one? How should I rewrite this? Else if. Now they're mutually exclusive. If all else fails, then go ahead and print out that number. Printf %d and the line I. Okay? Let's go ahead and run this. GCC demo. And verify. That's not it. There it is. 1, 2, 3 fizz. 6 fizz. 9 fizz. 5 buzz. 10 buzz. Uh-oh. 15. 15 is divisible by 3 and 5. Okay. Here's my first attempt. I should have taken care of that. Else if I mod 3 is 0 and I mod 5 is 0. Then I'll print fizzbuzz. There we go. And by the way, don't think that it's insulting to ever be asked to do something like this, right? When you eventually go to a technical interview, you might be asked to do something simple like FizzBuzz. That's just to get past the that 99%, right? Just take it in stride. Yeah, it's insulting if you know how to do it, but not everybody knows how to do it. You got to tell the difference, right? So that's not code. What do I need there? And, right? Ampersand, ampersand. All right, let's try this and see if it works. All right, remember it didn't work for 15. It still doesn't work for 15. 15 should be FizzBuzz. What's wrong? Yeah.
Well, it reads the
15 is divisible by 3, right? So that's true. The first one that's true is the one that gets evaluated, right? So the order matters. Most specific conditions up here, more general, more general, more general, the generalist of them all. The generalist of them all is going to be none of those conditions, okay? So let's move this condition up to be the first condition because that subsumes the other two conditions. There we go. Get rid of that. This will work now. It'll be correct. 15 is now FizzBuzz. The next one, 30, is going to be FizzBuzz. The next one, 45, is going to be FizzBuzz, et cetera, et cetera. Is there a way that we can improve this line? If something is divisible by 3 and 5, it's divisible by what? 15. Small optimization, but not absolutely necessary. Right? You still pass the interview, right? Now go talk to one of our folks, right? Again, if you think that that's it's insulting to have something like this, I went on an interview. Sure, I'll name Epic. They are a software company that does like medical software and stuff like that. They're based in Wisconsin. I did get an offer from them, but I turned it down. That interview was an entire day. They flew me out there. Many places will fly you out wherever you're going. Although now in today's world of Zoom, they're probably not going to pay for that anymore. But they did back then. And I spent an entire day, and half of that day was like technical interview stuff on a made-up language. It wasn't actually a made-up language. It was a medical software language that nobody would have ever heard of unless you were in that field. Google also flew me out for an entire day, and there it was more whiteboarding stuff, and that's traditionally what they've done. I don't know what they do anymore today, but you can Google for Google interview questions, and they're all just brain teasers, kind of puzzles that you solve on a whiteboard. Right? Okay, so there's your first interview question, FizzBuzz, right? And when you see it, if you see it out in the wild, go, great, I know how to do this, right? And then pay real close attention because they're probably going to, since it's over 20 years old, they're probably going to twist it around just a little bit, and you need to pay attention to those details. We've got time. Let's go ahead and compute the partial harmonic series here. Right? So what's the partial harmonic series? It's a series, right? A sum, right? Series, right? Yeah, not sequence, series. Where you take 1 divided by 1 plus 1 divided by 2 plus 1 divided by 3, et cetera, et cetera. So if you expand this out, what is this going to be? This is fraction of 1 over 1 plus fraction of 1 over 2 plus fraction 1 over 3 plus, and then it goes on forever. Right? Forever and ever, because it's an infinite series. But what I've done here is I've made this a finite series by changing it to end at n, which is an input. Because, of course, if we want to do the actual harmonic series, it's actually divergent, that it will go off to infinity, right? So there is no end to it, right? It will sum up to an infinite amount. But in this case, I've stopped it short, plus fraction of 1 over n. So if n is 10, then we have 1 plus half plus a third plus a fourth, dot, 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 plus 1/10. Okay? C or Java? Spoiler, it's not going to matter. 90% of it is the same except for the print statement. Java? All right. Let's compute the harmonic series here. First of all, I need my n. Let's just go ahead and keep it small as a test case, a small ad hoc test case here. Right? I know that 1 plus 1/2 plus 1/3 plus 1/4, I know what that is because I'm great at math in my own head here, and that's not true. I'm going to go to Wolfram Alpha and have it add that up for me. Right? 1 plus 1/2 plus 1/3 plus 1/4. There's my expectation that it should be 2.08333333. Right? So in double expected value should be, and I'm just going to have to estimate this, 2.08333333. I'll just go ahead and do it like that. Okay? Double actual value is equal to, we need to compute that. Right? We'll come back there. Right? All right, so help me out. What kind of loop do you want to do here? For loop, while loop, or an enhanced for loop? For loop, okay. For int I equals something, I is less than something, I plus plus. Fill in the blanks here. Actual value, I need to add to the actual value just like I did up here, right? 1, 1/2, 1/3, 1/4. So 1 divided by I, right? Just like the series is here. 1 divided by I, for I running from 1 up to n. Do you see the parallel there? This kind of a syntax was in mathematics for hundreds of years. Why do you think we have for loops that are written like this? Because it's highly influenced by math, right? All right, so I'll start at where? At 1. Right? I'll go up to and including n. So that's going to be, is that correct? Less than or equal to n. Right? And then I'll add I there. Now it's complaining. If I were in C, this would not be complaining at all. Why is it complaining before I show you the spoiler? Why is it not compiling actual value? I declared it, it's right there. What value does actual value have on line 13? It's uninitialized, right? Java doesn't allow you to play around with uninitialized values here, right? C will allow you to do that all you want, but it could be garbage. And garbage plus 1 is what? Garbage. Let's start this off correctly. How should I initialize this variable? 0, because it's a summation. There we go. All right, great. Printf system.out.println. We got plus actual value plus, does that match expected value? Question mark. There we go. Very, very informal there, right? We're going to formalize that up pretty quick here. We got 1.0. Does that match? Does it? System.out.println. No. Okay. So what's the problem? Yeah.
You gotta pass I as a number.
Exactly. 1 divided by I. 1 is an integer, I is an integer. So integer divided by integer is what? An integer. After we get past 1, everything is a fraction that is less than 1. Integer truncation makes them all 0. How could we witness that in real time? By firing up our debugger and taking a look at everything. Here's the actual value. It starts out at 0. Step, step. It now has a value of 1. Step, step, right? 1/2 has a value of 0. Right? It doesn't actually ever change. So, solution, typecast one of them as a double, or typecast the other one as a double by simply just point 0. And now, my answer is yes. Question mark? Is it? Well, this one has a lot of 3s. This one only has 4 3s. Are they the same? Let's test it. If expected value is equal to actual value, now let's not just answer yes or no here. Let's use code to say yes, they are the same. Right? Or no, they're not the same. And run this. And get rid of this yes question mark. No, they're not the same. But are they close enough? Yeah. How could I say that they're close enough? Well, I could go ahead and add some 3s over here, right? Pi out to 1,000,000 decimal points versus pi out to only 20 decimal points. They're not the same, but is it close enough? Yeah, in fact, I think that the old adage is that you only need 20 decimal points of pi to compute the radius of an atom versus the entire known universe or something, right? It's that imprecise. Right? So yeah, it's close enough. How could I say that it's close enough? I don't want to have this equals here, right? Close enough. How do I know if these two values are close enough to each other? Well, what if I took the difference? If the difference is small, then they're close enough, right? If the difference is less than, say, what's my tolerance? Say 1/10,000th. If they're within 1/10,000th, then it's close enough. Good. What if I switch these around though? Is it going to be close enough? Why? The difference is, oh, it is. Okay, darn it. It shouldn't have been. Actual value, expected value, what was the original? Tell you, expected value, there we go. That's still close enough, okay. Probably because, okay, I know what's going on, but that I didn't want to do that. What should I have done? Think calc, right? How is a sequence convergent? If it's close enough. But sometimes sequences go up and down, right? Sometimes their difference is positive, sometimes their difference is negative, but the difference is still small and good enough. How do I tell that these two numbers are good enough? By taking the absolute value of the difference. Right, there we go. And that will work regardless. Yep, close enough, close enough, close enough. Let's bump it up to 10. Now it's going to, I mean, I've hard-coded this value, so that's not going to be acceptable anymore. Does Wolfram Alpha do this for me? Sum of I equals 1 up to n of 1 divided by I. That's the harmonic series. Come on, more values. I want 10. 2.9 to ... There we go. Close enough. Right. How did I make that test case? I used an external tool. How am I writing my test case? I'm getting dangerously close to having a formal test case here, right? Where I have an input, I have an output, an expected output, I compute the actual output with respect to my code here, and then I make a comparison. If the comparison is close enough, we're good. It passes, right? Pass. Otherwise, that test case will fail. Right? And now you can see how I can automate this stuff, right? Just by writing code to automate all these tests. If I ever go back and make a change, right? When I changed it from, say, 1 to 1.0, I had an entire test suite here that I could automate and test that everything was okay. And that's what we'll do next week, after we've done a few more exercises. All right, have a good weekend.